Take a look at this client processing application. Notice the overlapping windows, the active drop-down menus, and the standard text fields. This is a finished graphical user interface, presenting a complex set of interactive elements in a way that feels immediately legible. There's a paradox built into this display. When an interface is engineered effectively, its underlying logic becomes invisible. The user rarely notices the structural rules governing where a button is placed or why a menu drops down instead of popping up. We have to make a clear distinction here. A system interface manages the raw exchange of data between different software programs. A user interface, the focus of our breakdown, manages the connections between the system and the human mind. Because it deals with human behavior, we measure the success of a user interface through a metric called usability. Usability tracks how quickly a user learns the system, how efficiently they complete tasks, and how rarely they make mistakes. Subjective aesthetics are a secondary concern. Intuitive design is the deliberate output of structural logic and behavioral psychology. This flowchart maps the chronological 5-step pipeline system analysts use to build that logic. We move from understanding users to organizing the interface, defining standards, developing prototypes, and finally, evaluation and testing. It begins by translating abstract human goals into concrete documentation. Analysts develop personas, characterizations of typical user groups, and write use scenarios, mapping the exact narrative steps a person will take to accomplish their work. To understand how this translates into the final product, we will work backward through this pipeline, stripping away the high-fidelity prototype down to its structural wireframes. A system built without these sequential engineering steps collapses when confronted with the friction of actual human behavior. Peeling back the polished application reveals this storyboard. It dictates functional flow, mapping how a user moves between menus. Unlike a data flow diagram tracking information, it plots the explicit paths a human takes through the software architecture. This structure satisfies the principle of content awareness. A user should always know where they are in the system, what information is being displayed, and how they reached their current screen. Analysts implement specific tools at this stage to prevent navigational disorientation. Breadcrumbs leave a trail of the navigational path, and active menu highlighting provides an immediate visual cue of the current selection. Navigating a complex database is a problem of geographic orientation. That geography must be mapped on paper before the programming begins. This schematic demonstrates spatial geometry applied to a single screen interface. Layouts typically divide the screen into 3 standard boxes. Navigation commands are anchored at the top. The active work area commands the middle. Status updates and secondary links are pushed to the bottom footer. The primary governing rule here is consistency. Keeping the size, shape, and placement of entering data static across multiple screens reduces the cognitive load required to operate the software. This introduces a tension with the principle of aesthetics. Designers face a constant trade-off, leaving enough white space to make an interface inviting, while avoiding losing the screen real estate required for important information. Spatial predictability allows users to build muscle memory. The interface becomes an extension of their own thought process. We populate the layout with functional elements using this wireframe diagram. Every element is subject to the principle of minimizing user effort, known as the 3 clicks rule. A user should move from the main menu to their desired action in under 3 clicks. But applying this rule reveals the usage level paradox. Heavy, frequent users demand rapid completion of tasks, while infrequent, novice users demand a system that is easy to learn. Resolving this conflict requires parallel architecture. The wireframe must provide broad, shallow menus and tooltips for the novice, while simultaneously embedding hotkeys and direct action inputs so the expert can bypass the menus. Effective wireframing is an exercise in minimizing the exact physical and mental steps required to extract value from a system. Once the user reaches their destination, the focus shifts to the input mechanism, how the system captures human data. Keyboard entry is slow and error-prone. Selecting from predefined categories using drop-down lists, radio buttons, or checkboxes is safer than typing raw text. The goal is to capture data at the source with minimal keystrokes. When raw input is unavoidable, the system applies validation checks in the background. Completeness checks ensure no required field is skipped. Format checks block text entries in numeric fields. Range checks reject data falling outside acceptable values. Watching a hand navigate a tablet reveals physical constraints that desktop engineering does not face. Touchscreens rely on standardized transform gestures, swiping, panning, and pinching, to move through content without the precision of a mouse cursor. This forces a layout inversion. Navigation controls must be placed at the bottom, and labels on top of those controls, so the user's hand does not obscure the central content area during operation. A system is only as robust as the data it absorbs. Strict input engineering is the frontline defense against database corruption. Finally, the system provides calculated data back to the human. This is the output mechanism. Output design is governed by the concept of information load. The rule is to provide all the information necessary to complete a task, and nothing more. Different contexts require different filters. Detail reports provide itemized lists. Summary reports compress that data for quick overviews. Turnaround documents output data that will eventually be fed back into the system. Selecting the correct format reduces the inherent bias of the presentation. Effective output design prevents cognitive overload by pre-processing raw numbers into immediate, actionable insights. No prototype survives human interaction without formal evaluation. Testing occurs in tiers. It starts with heuristic evaluation, where the interface is compared against a checklist of the core design principles to ensure structural compliance. Next is the walkthrough evaluation. The development team simulates movement through the exact use case scenarios outlined in Step 1, verifying that the actual navigational paths match the intended design. Finally, there is formal usability testing. This involves high-fidelity lab analysis where actual end users operate the system. Usability testing provides the empirical validation of the psychological assumptions made during the wireframing stage. The final language prototype is governed by 6 core principles: layout, content awareness, aesthetics, usage level, consistency, and minimal user effort. User interface design is an engineered pipeline. It requires precise documentation, structural diagrams, and set thresholds for interaction. A highly usable interface serves as a functional barrier. It protects the logic of the database from human error, while simultaneously protecting the human mind from the system's underlying complexity.